Can we generate random numbers per point in geometry nodes? How can we see the index number of points on the 3D view? Can we visualize attributes in the 3D view? Can this be done purely in geometry nodes? These are some of the questions that keep coming up all over forums and social media for some time now. And the answer is yes, you can. The problem is you have to build it yourself. Unfortunately, there is no built-in node for that. Today I'm excited to share with you how to do just that. Build an attribute visualizer with geometry nodes. Not just an index viewer, because indices are only positive integer numbers. With this setup, you will be able to view any range of float numbers, positive and negative. Not only view, but render them out also. And it will be super fast because it only generates instances. You can follow along and build the setup yourselves, or if you just need the node group to apply to your own projects, you can buy it for a small symbolic amount. I would appreciate it if you do. Let's get started. Start working with a mesh line for simplicity purposes. Lower the distance to 0.25. Leave the number to 10 for now. Add a reroute, group it, and name the group visualizer. Inside the node group, rename the input to geometry and feed it to a duplicate node. Each point will have a unique and unlimited amount of digits, so we'll have to duplicate each of them as many times as there are digits in the input number. More on that later. Now add an instance on points node. What will be instanced are text curves representing the numbers from 0 to 9. Write them down on the text field of a string to curves node, followed by a dot and a negative sign. The numbers to visualize will be floats, both positive and negative, so we'll have to use a dot to separate the decimals, together with a negative sign for numbers less than 0. Check the Pick Instance toggle so we can select a custom curve from our list based on its index number. As you see, each curve instance appears to be further offset to the right than the previous. Trying to fix this using the string to curves node parameters will be harder than it looks. Instead, we'll use the pivot point vector and invert its x coordinate using a vector math multiply node. Set x to -1 and leave the other two values to 0. Use a set position node to reset each curve before feeding them to the instance input. On the string to curves node, change the pivot point alignment to bottom center. Now all the numbers are overlapping. Let's offset them. Insert another set position, this time after the duplicate node. We'll offset each character to the left based on its duplicate index number. Since we'll make use of the duplicate index more than once down the node tree, to avoid cluttering the node tree with long and crossing connections, it's better to store this value into a named attribute and call it whenever we need it. Name this attribute simply duplicate index. Then call it using the named attribute node. Multiply it by some value that will represent the character offset amount. Feed the result to a combine XYZ to generate a vector and connect it to the offset input of the set position node. We can now change the character spacing at will. Frame these nodes and call them character offset. We will refine this offset calculation later, but it will do for now. This will be the core of the setup, and this is how it will work. We feed the number to our system, calculate its length of digits, and generate that many point duplicates. Each point will have a duplicate index number, and based on those indices, we will then pick the right text curve from our list and visualize the input number. For the sake of simplicity, let's lower the points number on our mesh line to 1. Also, For the moment, set the index instance to 0. Now all digits are represented by a 0. Let's add an integer number as input, for instance 15. It's made up of 2 digits. How do we calculate the length in digits of a given number? We use a logarithm node with base of 10. This returns the power of 10 a number represents. For instance, the number 125 is slightly greater than 10 to the power of 2. Use a viewer node to see the result. If we round this float number using a ceiling method, we get 3. That's precisely the amount of digits in the number 125. Try it yourself by entering several numbers. The system is not perfect though. There are some exceptions, but we'll make it rock solid. For example, numbers 0 and 1 return no digits. To remedy that, we'll add 1 before the logarithm node. That takes care of number 1, but 0 still returns no digit. Let's check if the attribute input is equal to 0. If it is true, the value is 0, so the output will be 1, else it will be 0. Let's add both results and feed the sum to the amount input. Again, store this value in a named attribute called length for later use. Now the system works, but only for positive integers. That's because no power of 10 returns a negative number. But apart from the negative sign, positive and negative numbers are identical. So let's make all negative numbers positive using an absolute node and take care of the negative sign later. Our little setup works fine for any integer input number now. Frame these nodes and call them calculate number length. It is time to visualize the correct digit for each duplicate point. Store the absolute attribute input value as a point attribute called conveniently attribute. We'll need to manipulate the instance index to pick up the right instance from our text curves. To calculate the indices, we'll call the point attributes we just stored. Use the named attribute node to call the attribute and duplicate index attributes. Now, we divide the attribute value by 10 to the power of the duplicate index and modulo the result by 10. Let me explain what we just did. All the duplicate points share the same attribute input value, but different duplicate indices. Each duplicate index will be an exponent to the power of 10. If we divide the attribute value by each of those powers of 10, we'll get the right amount of ones, tens, hundreds, thousands, and so on. Those ones, tens, hundreds, and thousands represent the indices of our curves. The modulo of 10 in the end makes sure that the curves to use are in the range of 0 to 9. Now frame these nodes and name them visualize digits. We now have a real integer number visualizer. How about float numbers? Well, we can easily convert float numbers to integers by multiplying them with some power of 10, right? Let's have a floating number, for example 125.25. Multiply the absolute value by 100 and we have the number 12,525 visualized. Try another number, 2022.136. The result is 202,213. The 6 is not visualized. To see it, we must multiply by 1000. Do you see where we're going? We need to multiply by 10 to the power of decimals we want to see. Add another integer number and store it as a named attribute called decimals. Raise or lower the number of decimals at your own will. Call this attribute by name and use its value as an exponent for the power of 10. Now we have all the digits of our floating number on the screen. Try another number yourself. You can see that we have the correct digits, but we're missing the dot that separates the decimals. To insert the dot means that we have to add still one more duplicate point in the middle. Adding another point is easy, but how do we insert it at a particular place? As you saw earlier, we can multiply our value by some power of 10 to offset its digit to the left or right. We'll do that again, only this time just for the integer part of the number. Let's separate the full number digits from the decimals. Use the truncate node for that. It will return only the full part of the number. We need to make room for one more digit between the full and the decimal part of the number, if there is a decimal part. So, if decimals are greater than 0, this will output true or 1. We then add this result to the decimal attribute value. Frame these nodes and call them full number. Duplicate the frame and its nodes. Call this frame decimals. Decimals won't be offset, so delete the add node together with the greater than. The truncate node returns the full part of the number, so to get the remaining decimal part, we need to subtract it from the whole number. To preview the decimals, replace the full number connection. Add both these results together, and you will have a number that represents both the integer and the decimal part divided by a 0. Test it yourself. Enter some random numbers. To replace that 0 in the middle with a dot, we'll modify again the instance index on our instance on points node. Use the decimals named attribute together with the duplicate index. At the moment we have 2 decimal numbers. If we think about it, we need to replace the third digit from the right. Indices start counting from 0, so the third duplicate point index is 2. Both the decimal value and the duplicate index match. Use a switch node in integer mode. If the duplicate index is equal to the number of decimals, and the number of decimals is greater than 0, the instance index will be 10. 10 is the index of the dot sign in our list of curves. If there are no decimals present, the number is an integer, so we connect the previous result. There you go. We have a correct form of a floating number. Frame these nodes and call them decimal values. Keep testing with other numbers. Scroll the numbers if you want. Let's take care of the negative values as well. To visualize a negative number, all we have to do is add one more to the number of duplicates. But first we need to know if a given number is less than 0. Store the result in a Boolean attribute called negative. Now call this attribute by name. If the number is negative, the return value will be true, so 1. If it's positive, it will return 0. Add the attribute value to the previous length of numbers and check the result. To replace the leading 0 with a negative sign, we'll again modify the instance index number. Call the negative attribute by name again, together with the length and duplicate index values. We only need to select the last instance for replacement. The last instance is the one whose index is equal to the length of digits -1. Not only that, but the input number must also be negative. Feed the result to a switch node. If the conditions are false, there's nothing to replace, but if the conditions are true, the last digit will be replaced by the negative sign, whose index in our curves list is 11. Magic, right? Go ahead and test yourself. Enter some number, then make it negative. We're almost done. There are some special cases when our setup doesn't work properly though. The range of numbers from 0 to 1 doesn't yield the right length of digits. Let me show you what I'm talking about. Let's take two numbers, for example, 2.5 and 0.5. If you multiply them both by 10, 2.5 returns 25, which our setup interprets as 2 digits. On the other hand, 0.5 returns 5, which our setup interprets as 1 digit. That breaks our setup. Enter 0.5 as the number input, then -0.5. You see, the leading 0 and the dot are not displayed at all. So we have to take those cases into account and modify our setup a bit to counter that. This modification will only occur in case the absolute input value is less than 1. Connect the absolute input value to a less than node. Enter 1 as the comparing value. Use this result to toggle a switch node. If the condition is false, connect the calculate number length frame result. If the condition is true, so the input value is less than 1 and there are decimals present, add a Boolean math, we want to have enough characters for decimals plus the leading 0 plus the dot. Add 1 to the Boolean output and then add the result to the decimals. In the end, feed the sum to the true input socket. Let's think this over again, slower this time. If the input value is less than 1 and there are decimals, the Boolean math node will output 1. This will add an extra character for the leading 0. We add 1 to have another extra character for the dot. After that, we add whatever number of decimals we choose. Now we can have an unlimited range of numbers we can visualize. Frame these nodes and call them less than 1 case. You may skip this next step, but from the aesthetic point of view, I would like to have less spacing between the separating dot and the numbers on both sides. We don't have proper kerning abilities in the text tool for Blender, but we can make some tweaking to our character offset nodes. You can offset the characters uniformly to the right by adding some value after the multiplication. But we don't want them to move uniformly. We want to be able to offset just the dot character and also everything that comes after it. The dot character is the one whose duplicate index is equal to the number of decimals. Every character after that has a duplicate index greater than the decimals. Let's test this. Call the named attributes duplicate index together with the decimals. Add a compare node and choose greater than or equal from the menu. Feed the result into a switch. If the result is false, the offset will be 0. But if it's true instead, we want to offset the characters to the right. Play with this value as you like. I will go with 0.15. As you see, this offset the dot together with everything that follows, but we want to offset everything after closer to the dot too. Duplicate the compare node and this time choose greater than. Now we have selected only the rest of the characters following the dot. We already offset them once, so we need to offset them once more. Add both compare nodes together and feed the result to a multiply node. Multiply the sum by 0.15 and connect the result back to the true socket of the switch node. Drag the value slider around and observe that we can now modify the distance between the dot characters and the rest. You have to keep in mind that all this calculation only takes place if there is actually a decimal number. So duplicate the decimals named attribute node and before the switch add a boolean add. Combine both greater than or equal results with the decimals value and replace the switch toggle connection. Frame these nodes together. How about overall scaling? If we scale the characters using the character size parameter, the distance stays the same. To have the distance and the character scale proportionally, insert a scale vector node after the character offset frame. Use the same value node to modify both the offset vector and the character size. Now you can scale the characters and their offset will change proportionally. We added several name attributes for this node group's internal calculations. It's a good idea to remove them in the end to keep the main tree outside of this group clean. So, add a remove attribute and type the name of each attribute you manually created into the text field. If you don't remember them, find them listed in the geometry node properties under internal dependencies. Again, we could have managed to build this setup using capture attributes too, but I believe this is way clearer to understand. All that our node groups need to be a fully working asset is to have proper inputs. Let's build them. Add a float input for the attribute to read. We'll need a decimal value for the float numbers. Make this input an integer. Set the minimum to 0 and the maximum to 3. In the end, add an input for the character size. Set the default value to 0.25, minimum to 0 and maximum to 1. Go ahead and replace the values in the node tree with the corresponding group input socket. There's the input attribute, the decimal values, and the character size. And that's it. We now have a fully working attribute visualizer built entirely using geometry nodes. It should be super fast because it generates instances instead of real geometry. You can use it to view certain attribute numerical values on the 3D screen while working, but you can also render them if you wish. Simply add a fill curve node at the end and that's it. Let's test this. First scenario, index viewer. Increase the number of points for the mesh line. Feed an index attribute node to the attribute input and set the decimals to 0. See? It works like a charm. Now add a UV sphere and replace the geometry input. Keep an eye on the calculation timings. See how low they are? Decrease the character scale to see the number more clearly. And now something more challenging. Use the mesh line again. Change the drawing mode to endpoints. Set the start location X value to -1 and the end to 1. add a set position node, combine XYZ, and feed a noise texture to the Z input. Now map the range from 0 to 1 into -5 to 5. Change the number of noise dimensions to 4D and animate the W value using a simple frame expression. #frame divided by 25 divided by 250. This animates each point randomly up and down. To visualize the number, add a position node, separate those XYZ coordinates, and feed the Z coordinate into our attribute visualizer input. If you want random numbers, you can map the Z coordinate to any other range. You can change the main geometry from line to grid, and the setup will update accordingly. I'm sure you can find many more use cases for this. Here is another example. I've scattered point into a volume cube and visualized their Z position. There you have it. An accurate, super fast, and easy to use attribute visualizer built using purely geometry nodes. Thank you for following me till the end. Consider buying the asset and, as always, if you like the video, share the knowledge.